Hi everyone, my name is Si Du. I'm very honored to be here and introduce our work, FairDisCo, Visual AI in Dermatology via Disentanglement Contrastive Learning. This work is completed by the University of British Columbia and Simon Fraser University. In this presentation, I'll first introduce the background and motivation of our paper, and then I'll talk about the method part, including our FairDisCo module and 3 widely used fairness algorithms. After that, I'll show our experiment results and analysis. Finally, I'll talk about the conclusion of this work. Cancer is one of the leading causes of death worldwide, and the skin is among the 6 most common organs invaded by cancer. However, early detection and treatment could considerably increase the survival rate of patients. Deep neural networks were introduced to automatically identify possibly cancerous lesions. They free dermatologists from tedious examination procedures and show a decent diagnosis accuracy. Despite their success, DNNs are vulnerable to biases that render their decisions unfair, such as skin color. For example, a recent study has shown that patients with darker skin experience a significant drop-off in diagnosis accuracy compared to those of light skin types. This limits the successful clinical deployment of these models. Up to now, few works tried to mitigate skin type unfairness in skin lesion classification tasks, given the following 2 reasons. First, most common skin lesion datasets like ISIC or SD136 lack skin images in very light and very dark colors. Besides, they usually don't have skin color annotations, but luckily, the introduction of some new datasets brings promise in this field. Our work is motivated by several reasons. Recent proposing skin datasets with various skin types and manually annotations make it possible for us to research skin type unfairness and fairness methods. Few works paid attention on the skin type fairness issue, and most of them simplified this experimental setting by only testing their model's generalizability on some skin types or coarsely grouping 6 skin types into light and dark. Fairness through blindness is a recent promising direction for mitigating unfairness in DNNs. It's achieved by complementing the target branch with a branch for classifying the sensitive attribute like gender or skin color. The framework captures semantic information to accurately perform the target task such as classification, while simultaneously minimizing the accuracy of the sensitive attribute classifier, so that the model could learn a sensitive attribute agnostic representation. However, some studies found those methods might hurt the representation learning of the target task. This is because after sensitive attribute information has been removed, the models might consider combinations of other attributes as a proxy and discard their information by mistake. For example, lesion color and visual features are critical for skin lesion classification, but are also useful for predicting the individual's skin type. To address this issue, we introduced contrastive learning to let the model retain discriminative semantic information about the target task. Therefore, in this work, we propose a novel framework FairDisCo featuring disentangled representation learning and contrastive learning to promote fairness and boost classification accuracy. To the best of our knowledge, we are the first to examine unfairness in skin lesion datasets using a variety of approaches and extensive experiments. We also employ 3 fairness metrics to better compare models, including 2 that we adapted from the binary sensitive attributes task. Finally, our FairDisCo achieves the best classification accuracy and fairness scores compared to other fairness-based methods and the baseline. The next is the methodology part. In the multi-class skin lesion classification task, the model is required to output a skin condition prediction based on an RGB skin image. And our goal is to model the likelihood without being affected by the skin type. We will introduce the proposed FairDisCo and 3 simple but widely used fairness approaches: reweighting, resampling, and attribute-aware. The intuition behind FairDisCo is to train a model to avoid capturing spurious correlations between skin conditions and skin types, and at the same time to learn semantic information from images. To achieve that, we incorporate 3 branches following a feature extractor. The target branch predicts the skin condition as the baseline classifier does. The sensitive attribute branch decouples skin type information from representations. The contrastive branch enhances feature extraction. I'll introduce the sensitive and the contrastive branches in detail. The sensitive attribute branch contains a classifier to predict the skin type based on the representation. We used a confusion loss on this branch to remove the skin type information from the representation. It calculates a logarithm on each position in the prediction vector and then takes an average on them. When minimizing this loss, the network is enforced to estimate equal probability for all skin types, which means the representations are free of skin type information. We also need to notice that the sensitive attribute branch might find a tricky solution like setting all the weights to 0. Then the classifier output is a 0 vector, and the confusion loss becomes the smallest even though the representation still contains skin type information. To avoid this issue, we add the skin type predictive cross-entropy loss, only optimizing the classifier. Although disentangled representation learning keeps the feature extractor blind to the skin type information, it might hurt the extractor to encode semantic information by discarding important features related to the target task that could indicate skin type. Thus, we add a contrastive loss that promotes inter-class cohesion and inter-class diversity to protect target features and improve the representation learning. We project representations into a low-dimensional latent space, and then calculate a supervised contrastive loss. The numerator is the similarity between samples in the same skin condition class, and the denominator is the summation of similarities between samples in different classes. By minimizing this loss, the network is enforced to keep as many factors to push samples in the same class together and push away those in other classes without considering different skin types. Finally, our total loss function contains 4 items. We use alpha and beta to adjust contributions of confusion loss and the contrastive loss. To better understand the unfairness issue and enrich our assessment of different fairness models, we studied 3 widely used pre-processing and in-processing fairness algorithms. Reweighting algorithm tries to make skin condition and skin type independent. The expected probability of our group is a multiplication between the probabilities of the skin condition group and the skin type group. However, we usually observed a lower probability due to the correlation between 2 attributes. To cut off the connection between them, we assign each sample a weight that is a ratio of expected to observed probability and multiply it with the cross-entropy loss. Resampling algorithm considers samples in the same skin condition and type are in the same group, and then oversamples minorities and undersamples majorities to create a balanced dataset. We set the sampling weight for each group as their inverse frequency. Attribute-aware algorithm tries to add skin type information to the model so that its prediction will not be dominated by major groups. The third part is experiment. We studied two skin lesion datasets, Fitzpatrick 17K and diverse dermatology images named DDI dataset. We use accuracy to measure models' skin condition classification performance. To quantify fairness, we adapt earlier fairness metrics, which were restricted to binary classification or binary sensitive attributes, to our multi-class classification and multiple sensitive attributes task. Predictive quality disparity measures the prediction quality difference between each sensitive group. Demographic disparity computes the percentage diversities of positive outcomes for each sensitive group. Equality of opportunity claims that different sensitive groups should have similar true positive rates. We calculate DPM and EOM across multiple skin conditions. On the Fitzpatrick 17K dataset, we first implemented the data statistics. Numerous data biases occur in skin type and skin condition. We follow Group et al.'s work to conduct two tasks on this dataset. For the in-domain classification, we randomly split the train and test sets. For the out-of-domain classification, we set 3 experiments. Each of them trains models on 2 skin types and tests them on other skin types. From the in-domain classification results, we make several observations. First, our baseline exhibits inconsistent accuracy that varies across skin types, showing the existence of skin type unfairness. Second, we observe the phenomenon mentioned in other papers where the accuracy of the major skin type group, like type 2, is lower than the underrepresented skin type group, like type 6. The ambiguous systematic pattern in accuracy across skin types could be seen in all the models in the table. Here we analyze the data and try to give some explanations for this situation. The first reason is domain distribution diversity across domains. The Fitzpatrick 17K dataset is collected from 2 domains, derm and atla. As illustrated in the figure, derm has the most samples in type 2, the fewest samples in type 6, and a higher average accuracy. But atla has the most in type 4, the fewest in type 1, and a lower average accuracy. The diversities of distribution and classification difficulty across domains conceal the real pattern when we directly train models on 2 domains and only report the overall accuracy. Besides, different diagnosis difficulties across skin types also causes the problem. The figure shows that the baseline's prediction and ground truth in benign class have similar distributions. Type 2 has the most and type 6 has the least, indicating the model's prediction is affected by skin type. However, the correctness distribution is quite different. Type 2, 3, 4 have a similar number of correctness even though type 2 has more benign predictions. Then we could hypothesize the images in type 2 might be more challenging to classify than those in type 4 and 5, confusing the relationship between accuracy and statistical data distribution. Third, the small group size might make the test results unreliable. In our test case, some groups only have a few samples, thus a correct or wrong prediction will significantly impact their accuracy, making the results of underrepresented groups untrustworthy. Come back to the in-domain classification results. We could find fairness methods show a promising performance compared with the baseline, and in addition, FairDisCo achieves the highest accuracy and fairness scores. It also outperforms FairDisCo without the contrastive branch, showing the effectiveness of contrastive learning. We further visualize the main terms of fairness scores on the benign class. The following two figures show that the baseline has diverse values across skin types, indicating the model is affected by skin type information. However, FairDisCo presents little variation across skin types and boosts the minor skin type group's benign prediction rate and true benign rate, showing our model reduces skin type unfairness. Another task on the Fitzpatrick 17K is the out-of-domain classification. From the table, we could find the baseline has high accuracy on those skin types similar to those it is trained on. This reveals the model's decision-making is relevant to the skin type. In addition, FairDisCo is the second best among all the algorithms. We think its inferior performance compared with FairDisCo without contrastive learning is because the contrastive loss only helps to learn better representations of skin type groups appearing in the training set. However, the out-of-domain classification task has a large diversity across skin types between the training and test sets. For the DDI dataset, we also analyze the data first. It contains similar skin condition data in balance like the Fitzpatrick 17K dataset, but less skin type bias. We follow Danny Shu et al.'s work to conduct an in-domain classification task. In this experiment, we further add area under the ROC curve named AUC to measure the classification performance. For the baseline, the major skin type group T34 is more accurate than the minor groups T12 and T56, showing it ignores the underrepresented groups. Besides, all the fairness approaches except attribute-aware algorithm outperform the baseline. And our model FairDisCo achieves the best classification performance and fairness results. Its superior performance compared with FairDisCo without contrastive learning further demonstrates that the contrastive loss plays an important role in learning a better semantic representation. The final part is a conclusion. In this work, we improved the fairness and classification accuracy by proposing a novel deep neural network FairDisCo with disentangled representation learning and contrastive learning. Besides, we compared the baseline and FairDisCo to three widely used fairness techniques: reweighting, resampling, and attribute-aware. We also proposed three fairness metrics for our task, which could also be applied to other fairness tasks, and conducted extensive experiments on two datasets. Our results indicate that the datasets have skin type bias, and fairness methods could diminish the discrimination. Finally, our proposed model FairDisCo achieved the best overall accuracy and fairness on in-domain classification tasks, and surpassed the baseline on the out-of-domain classification task. That's all. Here are our paper and code links. Thank you for your listening.